Good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome once more Professor Richard Elliott. He's currently a Professor Emeritus at the Chemical, Biomolecular, and Corrosion Engineering program at the University of Akron. His research interest is mainly focused on molecular simulation, thermodynamics, polymer physics, and phase equilibria. Besides, he is the co-author of the thermodynamic section of Perry Chemicals Engineer Handbook, and also the co-author of the upcoming sixth edition of The Property of Gases and Liquids. I think he needs no further introduction. He has been a great friend of the Atoms group and has been with us since the beginning of the seminar series. So once again, welcome back, Professor Elliott. Thank you so much for accepting another invitation, and please feel free to start your talk.
Okay, so thank you very much for inviting me back. And as you mentioned, I made this presentation, made some presentations here before. And as I get older, it's harder and harder for me to remember who I've talked to about what and what we said exactly. So I made a little list here of all the different ones. And it's hard. It gets a little difficult because we have new students coming every time, and they may not be they may not have even seen any of these things, and then nobody remembers everything that everybody says. And so I'll do a little bit of review here, but mainly just about this topic that I introduced the last time we talked, which was MEM1, and that's been about a year. So if you've forgotten some things, that's fine. And I'll just be focusing on a kind of a narrow part of that and then extending it to MEM2. And so what's the two about? When you have two things, we're going to go through some algebra, and we're going to see that two things result in separate distinctions of acidity and basicity. And when we do that, this TPT1, very mathematical, very math physics, cluster integral expansions, everything very rigorous, it transforms into a theory that brings into consistent representation 100 years worth of solution theory and thinking about the nature of molecular interactions, going back to G.N. Lewis in 1923. And so we're going to use his definition of what is an acid and what is a base, and that relates to an electron donor is a base and an electron acceptor is an acid. And so this is a little bit more general than the just hydrogen donor and hydrogen acceptor. So it's a little bit more convenient in the general formulation. So in the outline then, I'll give you a little history of beyond what G.N. Lewis said. There's a very nice article that I'll direct you to. And then we'll talk about some characterizations in the past. And then I'll walk you through the algebra. So mainly what I'm going to talk about today is an algebra trick. Then that leads to a lot of characterization of what are those numbers that have to fit into the theory. So let's go through the history then really quickly. There's this article by Appelblad in 2007, and he goes through history, even going back to Boltzmann in 1884. If I knew this, I forgot it, was that Boltzmann actually figured out the chemical theory of second virial coefficients long ago. And Dolezalek gets a lot of credit for doing that in a lot of the chemical engineering literature. But according to Appelblad, Boltzmann did it first, which is not uncommon. Boltzmann did a lot of things first. So I thought that was really interesting. fast forward to Guggenheim and quasi-chemical theory, and recently I've been really developing a lot of more appreciation for quasi-chemical theory, because I've recognized it can be done off lattice. I've recognized its role in Cosmo-ORS theory, and how that is a very modern theory, but it derives the thermodynamics of it derives from this very ancient theory, going back to Barker, who recognized that if you have a cubic unit cell with 6 faces, and one of those faces is very strongly interacting, like a hydrogen bond, and the other 5 aren't, then that gives you something that's stereospecific and short range, because all of those interactions are short range. And so that's very much like a hydrogen bond. So there's a lot of hydrogen bonding that goes into quasi-chemical theory historically. And then Paniatou and Vera extended quasi-chemical theory to the multi-component setting. Paniatou went on and did some work with lattice fluid hydrogen bonding, and he's been trying to unify many different hydrogen bonding theories. The chemical theory really started with Boltzmann, but was extended to this continuous association theory, where we do K1, K2, K3, Kempter and Mecke, and then that led to ultimately this Heidemann and Prausnitz theory, which I liked a lot when it came out. And then in 1977, Camelot and Taft developed this linear solvation energy relationships that inspired Muscat by Eckert and co-workers, and they formulated their contribution to the association a little bit differently. And one of the things you can say about this is everybody who has looked at this hydrogen bonding problem and tried to quantify their acidities and basicities comes up with different numbers. And guess what? I'm going to come up with different numbers too. And I hope to explain why maybe that everybody gets different numbers. But the overall problem is a lot like the blind man and the elephant. Do you know that story? So the blind men hear there's an elephant in town. They don't know what it is. They want to figure it out. So they go, and it's a big animal. So each blind man touches a different part of the elephant, and they all arrive at different conclusions of what that elephant is. And you can Google the story and find out how it ends. But that's the basic idea. Different observers come to different conclusions. And so that's a big part of the problem, I think, with looking at acidity and basicity. Well, one thing that I like about this Muscat theory is, and I wrote about this in 2010 in Chem Education, is the Muscat theory is really easy to understand for undergraduates or sophomores, anybody really, I think. And because they've heard of hydrogen bonding in their biology class, in high school, and so they know there's something about acidity and basicity and things. When an acid gets together with a base, they bind. Well, what Muscat theory says, I'm using the word theory generously here, is that if you have acetone, for example, which is a base, but its acidity is 0, and you combine that with chloroform, which has an acidity, but its basicity is 0, and you put that into this equation, then you see that alpha 2 is a positive number minus 0. Beta 2 is 0 minus a positive number, then you get a negative number here, and that will give you a negative deviation from ideality. And that's exactly what we see when we mix acetone and chloroform. But if we mix methane, let's say, with water, and water has very large alpha and beta, so it's self-associating, then alpha 1 is 0, beta 1 is 0, and we get a positive number times a positive number, we get a very large positive deviation from ideality, and that's exactly what we expect to see with water and oil trying to mix. So this theory of Muscat gets the sign correct, and that's where the theory ends, okay? The rest of it is all just phenomenology, hand-waving, and empirical fitting especially when it comes to what are the values of these alphas and betas. So that's one of the problems we'll talk about today. And also they throw in this Xi1 parameter, which is just a kind of a magical equation that's very empirical that just does whatever it needs to do to fit the data. And so that's the extent of Muscat theory. Well, when you look at TPT1 theory, in some ways it's not so different. It has the same picture of these acids and bases being very short range and stereospecific, and they're blisters, but Vertime gives a very mathematical definition of what this bonding volume is and what that association energy is, and it comes out basically in this form, where these x's describe the extent of that the fraction of monomer, okay, the fraction of the bonding sites that are not bonded. So it's a little bit of a backwards concept, but once you wrap your head around it, it's kind of the monomer fraction. And so the conceptual picture for Vertime's picture is not so different from Muscat or all these other different representations of hydrogen bonding. And a key quantity here is this delta quantity. I want to review what that means in a minute. So what about TPT1 compared to these separations of cohesive energy density theories, Muscat, simplified SCED, all the SCEDs, and then linear solvation energy relationships from which this SCED perspective kind of derives? Well, as I mentioned at the outset, Vertime's theory is much more rigorous, much more mathematics, and the cluster diagram expansions are enumerated. At the same time, multiple people have shown that if you make the right assumptions, for example, the change in heat capacity that occurs when the bonding happens, then nobody really knows what that is. You could say that delta Cp over R is equal to -1. That's one common assumption in chemical theory. Or you could say that it's 0. That's another common assumption. Or you could say it's what Vertime says. Since nobody knows, we might as well use Vertime's assumption, because at least it has this cluster diagram expansion behind it. If you want to enumerate what each individual oligomers are, you know, like a methanol dimer bonded with an ethanol monomer, okay, we can figure out what all those populations of oligomers are. On the downside, you need to recognize that this system of equations is actually a large system of equations. The more types of acceptors that we have, the more types of donors we have, we get a bigger matrix that we have to solve. At the same time, if we have more components, the matrix gets bigger again. So it goes up as the number of components squared times the number of acceptor types times the number of donor types. So it's kind of like a four-way matrix. And you can easily imagine that if you had 5 components, that's going to be very slow to solve. And if you're trying to do that in a process simulator, every time you do a z-factor iteration, you could be in trouble. One other point is that, and this is a little bit of a subtle point, is that in Vertime's theory, he never really designates anything about an acceptor energy or a donor energy individually. You always need to know what's the acceptor donor energy. And we don't really have any good ways of predicting what those are. So that's one of the ways that MEM2 can help us. Before I get into that, I want to reiterate, in case you might have sort of put it in the back of your mind, what is this delta quantity? Because a lot goes into it. When Vertime originally derived it, he went through the integration, which is a very detailed integration over all orientations and distances. And it so happens that it comes out to have the units of a volume. Chapman, when he formulated his SAF theory, he said, well, let's just approximate this G as a hard sphere contribution. And then we can do a lot more calculations more conveniently. But we shouldn't forget, it is an approximation. And so it's a pretty good approximation, better than I originally appreciated. And we did some simulations to check that out way long ago. And essentially, it's as good as it is because hydrogen bond is so stereospecific. So these small interaction sites essentially are like a horse with blinders on. They can't see that this tail, this could be methanol here, but it could be, if you added more segments here, it could be octanol. And this little bonding site with its blinders on can't really see how long that tail is. So it doesn't really matter. It only matters what's coming into its frame of reference, okay? What's coming into that little window that it can see. So that's why it effectively acts like it's an equivalent isolated sphere. It's a good approximation, but it's still an approximation. And to demonstrate that, I did some experiments to show that if you were to mix ortho polyvinyl pyridine, we see where the nitrogen's close to the vinyl group, okay, with polyvinyl pyridine, okay, so if the nitrogen was over here, if you were to mix the polymer made from those polyvinyl pyridines with polyvinyl butyral, which has a funny name for what it actually is, then you can actually see a difference in the phase behavior. And it's basically one phase as you cool it down. So that's one thing you need to realize. And that's happening because the hydrogen bonding is becoming so strong that it's overcoming the polymer incompatibility and making a single blend of that polymer. And that occurs, you have to go to a lower temperature for that hydrogen bonding to take over when it's in the ortho position, because that nitrogen site is not as accessible. And in that way, we can actually put numbers on how accessible, how much we need to correct this G factor by in order to get the right steric representation. And what that's all going to show up in is this KAD, because anything that's constant just gets lumped into the KAD. So I want you to sort of understand and remember that steric factors are a part of this. They can be close to 1 because of the equivalent isolated sphere approximation, but they may not always be 1. And we have the capability to adjust for that. But we shouldn't do too much adjustment. The KAD has some physical meaning. We shouldn't treat it as a random number. We should pick something that represents, let's say, methanol, all right? Use that for everything that looks like methanol. Ethanol, butanol, those things, certainly ethanol, propanol, look enough like methanol, little short chain, that from the equivalent isolated sphere perspective, we should use a constant value of KAD. And if we can minimize the number of parameters in our theory, we're going to be a lot better off when it comes to characterizing these. So let's go back to MEM1 and make a brief review of that. And the thing I want to point out in this set of equations I showed you before is that I factored out this XAI because it's not a function of J or L, okay? And I want you to pay attention to this subscript. These green highlights, they mean you should remember that, okay? I want you to remember that if you can. And the key point here is that this is a sum over J's and L's, and the only place that the I appears is in this delta quantity. And what is this delta quantity? Well, it's this Gij, KAD, exponential of alpha ij, okay, exponential of epsilon ij. Well, what if I could separate that rho delta quantity into an I part and a J part, where the alpha, so if it was II, okay, if this was I and that was I, it would be this quantity, right? But it would just be an alpha, an epsilon I AD for II, all right? So let's say methanol and cyclohexane. Then methanol is component I, it would have a non-zero value of alpha. Cyclohexane, its epsilon of self-association would be 0. E to the 0 is 1, 1 minus 1 is 0, delta is 0. Okay, so we can easily understand how this alpha quantity would work out to be separable in this way. And as an approximation, here's the amazing thing that happens when it's separable. I plug this definition in here, and now that alpha I can be factored out of the double summation. So let's write it that way and rearrange so that the xi, all the I parts are on the left-hand side of the equation. Then we see that this equation sums over all of the j quantities. When you sum over all the quantities that you're summing over, you get a scalar number. It's just a number. All right, let's call that number FAD. And the funny thing that happens is this FAD has no subscript, but the quantity on the right-hand side does have a subscript, which means that all of these x's can be solved as soon as I have this one quantity FAD, and that can be solved from this one nonlinear equation. We can use that for Newton's method, and then we get 1,000 different values of this XAD quantity that characterizes the extent of bonding. And it's all because of this kind of subtle, sneaky alpha quantity in the way that we've defined it here. Well, that leads to a number of implications with respect to infinite dilution activity coefficients. One of the things that you find in this symmetric version, let me emphasize one of the reasons why this is symmetric, is because the number of acceptors is equal to the number of donors for each component. Let's walk through that. Let's use a two-site model for methanol. All right, so it's got one acceptor and one donor. All right, fine. So 1 is equal to 1, and methanol is symmetric. What about cyclohexane? Fine. It's got 0 acceptors and 0 donors. So 0 is equal to 0. Everything's fine. So that mixture is completely symmetric. Everything's fine. And in that case, we get some really simple solutions, one of which, for any associating compound like methanol, F is almost practically equal to 1. We don't have to solve the equation. Just put 1 in, and you're good to go. All right? If it's at room temperature or 100 degrees Celsius, somewhere in that range. And in that, another thing that happens is we get an exact result for the infinite dilution activity coefficients in this scenario. So if you're in a real hurry, you don't even need to solve any equations. You could just plug and chug and you're done. And the result that comes out of that in terms of the phase behavior is really a big improvement. And this is what sold me on TPT1, because I had been using a lot of different theories to try to describe a system like this. Nothing with any kind of reasonable value of local composition parameters that I could tie to statistical mechanics could give me this kind of representation of the phase behavior of cyclohexane plus methanol. So Ping Robinson is representative of any of those mean field theories or perturbation theory types of phase behavior that you're going to get. And you can see it's just bad. And whereas the combination, this particular one is the ESD model combined with the MEM1 model, it gives you a pretty good description of the LLE and the VLE simultaneously. So that's a practical demonstration that, yeah, we should be interested in this result. Then we come to a problem though. What if you wanted to mix acetone with your water? That's going to be asymmetric because acetone has a donor site, but it doesn't have an acceptor site. So Na is not equal to Md. Now we need to come up with some kind of a generalization. And that's really what MEM2 is about. It took me 30 minutes to get here. Oh wait, no, only 25. We started 5 minutes late. So I'm going to make the same basic argument that we can separate this rho delta quantity into an alpha and a delta, and two alphas, okay, an alpha A and an alpha D. But look at the superscripts and subscripts here. You can see that I'm being much more specific here. So let's go back to the symmetric one. You can see when it was a symmetric system, all I worked out was if you just had one donor type and one acceptor type on each molecule. Here, I've generalized it so that you can have something like methanolamine, where you've got an amine site and an alcohol site on the same molecule. Okay, so this is completely general. And I've got to keep track of, is this the acceptor on molecule I or the acceptor on molecule J? So I always write it this way. If I want to talk about the alpha for the donor on molecule I, then I will write that as alpha DK sub II. All right, so it's a little bit more specific, and you have to be careful with these superscripts and subscripts. But when you do that, you find, again, you can still factorize these double summations, still comes out to be a scalar number, and you still end up with these subscripted quantities on the left-hand side in terms of a scalar number on the right-hand side. And you can solve for an infinite number of acceptor and donor extensive association, just knowing not one quantity now, but two quantities, Fa and Fd. And so here are the two equations that you have to solve. They're kind of beautiful equations, in my opinion. You've got an Fa on the left-hand side and an Fd on the right-hand side here. And below it, you have the mirror image with Fd on the left-hand side and Fa on the right-hand side. These are two coupled equations. And so, yes, it's a little bit more complicated to solve. But when you do, you get an infinite number of solutions for these extensive association for all of these things. That's a much faster problem to solve than if you were solving the full system. To demonstrate that, I optimized this binary VLE database that is discussed in chapter 8 of the properties of gases and liquids. So this was the database about 200 different binary mixtures that we use to evaluate which theory is the best, okay? And so if I do that, and these are just binary mixtures. Imagine if it's got 5 components, okay? 5 is not much in a process simulation. But if you have the full simulation, the full calculation using just for a binary mixture, 200 binary mixtures, the optimizing the binary parameters for all 200 mixtures, to do that with the full TPT1 formulation, that takes 93 minutes. But if you do it with the MEM2 method, same basic chemistry, same math, you're doing it in 2 minutes. That's a huge difference. Now, how much it is slower, though? How much slower is it than, let's say, the Ping-Robinson method? So MEM1 is about 3 times slower than the Ping-Robinson method, and MEM2 is another factor of 2 beyond that. So it's still slower, okay? So it's about 6 times slower than solving the Ping-Robinson equation. You might notice that, but computers are getting faster and faster, so there's a good chance you probably won't notice that, depending on the size of your process simulation. There's one more point that I want to make, or a couple of points that I want to make about how I actually solve this set of equations. And there are implications for broader questions that I just want to put out there and say these are like on the horizon. If you think back to your chemistry, your freshman chemistry class, maybe even first year in college, maybe even high school, you probably heard that a hydrogen bond has an energy around 5 kcals per mole. A van der Waals interaction is around 0.5 kcals per mole, and a covalent bond is around 50 kcals per mole. Big round numbers. All right. So what if we just said, okay, that's fine, we believe you, high school chemistry teacher. Let's use 5 for everything. If we do that, then that means that all of these alphas are the same. And if all of these alphas are the same, and FD is whatever we're solving for, then we can factor that out of this double summation. And we end up with this quantity that's in the numerator is just by itself, and this constant factor of alphas is in the denominator. And I'm going to hedge a little bit because I'm just going to say, well, it may not be exactly the same for every compound, but there's definitely, it must mathematically exist, some mean value, okay, that makes this factorization feasible. And so in some sense, this is really just a definition of the alpha mean for D. And it's also a definition, as I've written here, for this FA naught quantity. What is FA naught? Well, it's a mole fraction, so some sort of concentration. Concentration of what? The number of donors. The number of donors on component I and the Lth donor, okay? So think about a protein, all right? So it's going to have just one molecule, but many, many, many different types of donors, all right? That's not a problem. Just talk about the number of donors of each different moiety, multiply by the mole fraction, which is probably 1. And then, but we have to weight that by this square root of alpha quantity. So what is this? In the end, one simple way to think of that is this is just a donor concentration. We don't have to say what it's attached to. That's what I'm getting at. Just compute all the number of donors over all the different molecules, and there you have it. And the FD naught is the similar quantity with A's in it, okay? So this way we've defined some alpha mean and alpha D mean, alpha A mean, alpha D mean. And when we rearrange that equation, because the FA here, I can solve for here, substitute it in, get a quadratic equation, then I get an exact solution for FA and FD. That gives us an iteration scheme for guessing alpha A mean and alpha D mean, iterating on those. Then when we solve the FAs and FDs, we can recalculate the new alpha means through this equation. Then that will give us the successive substitution iteration for the next one. And this converges quadratically because we've used a quadratic equation to provide us the next FA quantity. Okay, so that's how the calculation actually goes. Not as a pretty quick coverage. One key point is it would be an approximation to just go ahead and stick with this grand master approximation. They're all equal. The problem is you won't get bond-sign balance if you do that. And so you're essentially iterating until you get the number of bonded acceptors is equal to the number of bonded donors over the entire mixture. That must be true. So those are a couple of points. One more point I would make is that this FA and FD then are single quantities that characterize the amount of hydrogen bonding after the solution has converged. So those are going to be functions of concentration through the, let's say, imagine a globular protein. And so we can imagine that there may be regions where there's more hydrogen bonding, like beta sheets and alpha helices. They have to get together. They have to have hydrogen bonding concentration there. And then maybe you have a layer where there's not so much hydrogen bonding. And this may give us a sort of framework of, or a scaffold, okay, of how we can imagine that protein folding and forming its different spheres of concentric spheres of hydrogen bonding and not. As I mentioned, there are many, many measurements of this characterizations of acidity and basicity. The one that I used when I was using MEM1, I just was trying to characterize self-association versus non-self-association. And I found you could actually get a good feel for that just by looking at vapor pressure data. So if you fix the value of your bonding volume, then you could just vary one parameter, this epsilon for A and D bonding together, and adjust that until you get the best fit to the vapor pressure behavior. And this is a log scale, so even though this looks like a very small deviation down here, it's actually about 20% deviation. So that's a big number. You can definitely see that. The problem is here is that I can't distinguish epsilon A from epsilon D based on vapor pressure because I've just got that one measurement. In order to see whether it's acid or base, I have to put it in contact with something that's acid or base. Another way of looking at this going to Cosmo RS is look at your sigma profiles, and they have some guidelines for whether you're past this dotted line, then, okay, we're going to call that a proton donor, I forget. If you're past it on this line, there's a proton acceptor. And so these can be used, maybe the area under the curve or some other designation, to calculate the acidity and basicity of the molecules that way. Another one that I like a lot is this Camlet and Taft method. They use spectroscopy with, let's say, a molecule like this. They put that standard, I think this is used as a standard base, and they put that in contact in very dilute solution with carbon tetrachloride is 99%. Then we put this molecule in contact with, let's say, chloroform at 0.5% of each, and measure the shift of this fluorine, this FNMR. And based on the amount of the shift, we can characterize, okay, chloroform is this amount acid, then the next acid and the next acid relative to that, based on how much this shift is. So that's the basis of this LSER theory. And this is a website where you can find a large number of measurements of those types of compounds that I just recently became aware of. So in this way, we see that the concept of acidity and basicity within TPT1 can be consistent with all of these other types of inferences. But keep in mind that every observer seems to come to a different conclusion about how acid is this site versus how acid is it when you measure it this way. So let's figure out a way to characterize it within TPT1 and MEM2. Let's start with acetone and chloroform. Again, this is an arbitrary choice. But acetone and chloroform are pretty famous. We recognize those when we talk about this problem. And it turns out a lot of experimental measurements have been made with acetone and chloroform too. So to get started, we're going to take the ratio of alpha over beta from this Muscat theory, another arbitrary choice. But once we make that choice, we only have one parameter that we need to vary. We guess epsilon A, then we get epsilon D from the ratio, and we just start with 0 and make it bigger and bigger and bigger until we match the VLE curve. Then once we have epsilon A for chloroform, then we can either make a guess and predict it from Muscat, or we can just vary the value of epsilon A relative to acetone. So get a mixture of acetone with that compound, and then vary the epsilon A until we match the VLE for that new mixture. And that's what I did in this first paper that I gave you the reference for on the first page. And so let's do that. Here's what acetone and chloroform look like. And you can see I kind of shifted it down the whole thing because the vapor pressures are off a little bit. But otherwise, this is just, following the procedure, matching the VLE data. Then once we've characterized acetone and chloroform, then we've got this, then we can use that chloroform energy and characterize diethyl ether, tetrahydrofuran, MTBE, and then show the amount of deviation in the VLE behavior for the MEM2 compared to MEM1. And what you see is there isn't much difference. Why is that? Because in both cases, I'm still letting Kij be a freely adjustable parameter. Okay? And so when it comes to making a correlation and Kij is adjusting to do the best you can, then you don't see much of a difference. But now let's go into predictive mode. Since I've characterized THF using chloroform, and I've characterized halothane using acetone, then I can make a prediction of what's going to happen when I mix THF with halothane and use Kij as 0 for everything. Then what you find is you get a much better prediction when you use MEM2 instead of MEM1. Okay, and so you're getting this predictive capability, and that's an important point because it means that this acidity and basicity that I've characterized using methanol and acetone and chloroform is transferable, and I can use it to characterize predict what's going to happen when I mix some other things. So we're predicting binary properties from single compound characterization. So that's a big step. Then we can do a larger evaluation and see if we do a comparison like in the PGL, what happens if we do a big mass evaluation. And what we see is that we get a slight improvement. It's only slight because in both cases, there's a Kij to kind of fudge everything. The improvement when we get to aqueous liquid-liquid equilibria is more significant. And you can see that it's almost as good now as Uniquac, which is a 2-parameter. Fine, that was the end of paper 1. Okay, let's talk about expanding and extending to more and more types of mixtures and types of interactions. Well, if we just use vapor-liquid equilibrium, what we find is there's not much difference in the vapor-liquid equilibrium if I use 2 very different values for this hydrogen bonding energy or acidity or basicity, okay? Same thing happens with chloroform and pyridine. I mean, pyridine has to be a strong base. There must be some difference, but you can't see it when you just look at vapor-liquid equilibrium. In order to see it, you have to look at your excess enthalpy. And this harks back to many of the other methods of characterizing hydrogen bonding, which use calorimetry to do that, all right? And so it's not the first time that somebody's used calorimetry to characterize these donor and acceptor tendencies. And when you do that, this combination is really sensitive. And so we've got a tool now of a theory combined with some experimental measurements that gives us a very sensitive probe into what the molecular interactions must be. Compound of very interest is carbon dioxide. Is it an acid? Is it a base? I guess it's carbonic acid. Everybody says it must be an acid, right? Well, but if you look at Jobert's classification of the different types of mixtures, he thinks CO2 is a base. And maybe it is. It's got carbonyl groups. How can we decide? Well, it turns out vapor-liquid equilibria can't tell us the answer. But if we look at the excess enthalpy, we get a very clear indication. It has an acidity. The number is 1030. Is that really true? How can that be? Where is the acidity of this CO2? You know? Well, we could get an indirect justification that maybe that's true by looking at a compound similar to carbon dioxide, and that's CS2. Think about your periodic table. S is just below O. It's got another quadrupole moment, and we see that CS2, using the same basic procedure, is even more acidic than the CO2, and there's no hydrogen in there, okay? And so there's some sort of consistency here between what's happening with the CS2 and the CO2, and it's showing up in our excess enthalpy data. But all is not sweetness and light. It's not always so simple. Whenever you have a self-associating compound like water or ammonia, it gets much more nebulous to make a judgment of, you know, how acidic is it. And so what I've shown here is the VLE for acetone and water. We could definitely eliminate some basicity because we know that chloroform doesn't mix with water, okay? It forms LLE. So the chloroform and the water don't like each other too much, so there can't be too strong of an interaction that way, but acetone and water mix. So what happens with the VLE is if I assume that it's the same acidity as it is basicity, because it must have, because it does self-associate, and I see that in the vapor pressure, then a value of 1 to 1 gives us this VLE, which isn't too good. A value of 2 to 1, that's pretty good. So why am I putting in this 1.5 value? Because when we look at the excess enthalpy, a value of 1 to 1 gets the closest to the excess enthalpy, but none of them is good. We can all admit that. So the excess enthalpy is telling us that it ought to be 1 to 1, maybe even 0.5 to 1, and the VLE is telling us it ought to be 2 to 1. So what do we do? Well, For me personally, I value the VLE more than the HE. It has a bigger impact on my process simulation. And so I picked a number that's 1.5. And again, that's very arbitrary. What about ammonia? Turns out there isn't any HE data. Think about that. Ammonia is so important for fertilizer, for refrigeration, for the hydrogen economy, and we don't know anything about it in terms of its excess enthalpy. One more thing I have to tell you about is a kind of caveat, and that is I've only shown you, for the most part, one molecule, let's say acetone, bonding with the other molecule. And then once I do that, I've characterized the acidity of that molecule for all time. Yeah, that's a little oversimplification. And here's an example of that. And I'm using chloroform now, or I'm trying to characterize what is the basicity of toluene. And when I mix it with chloroform, I get a very clear number. It's 300. Okay, fine. And then for some reason, I got suspicious about that. And I said, well, what if I mixed it with, instead of trichloromethane, let's mix it with dichloromethane and see what happens then. Will it give the same answer? I was thinking it would give the same answer and life would be good. Unfortunately, it's a little more complicated than that. Instead of 300, I get 1800 when I use the dichloromethane to characterize this. When I use dichloroethane instead of dichloromethane, I get a different number, 1060. And when I use methanol instead of any of these chlorocarbons that have just asymmetric acidity, instead use a self-associating compound, even 0 is not low enough. And so different interactions of the molecules give you different inferences, okay? And so what we have to do is add up all the different inferences in some way, I'm saying add, and average them, okay? And that's gonna give us some average acidity or average basicity in the case of toluene. But we have to remember that the individual ways that these individual pairs of molecules combine could be different from that average. And I think that's why so many different observers get so many different answers, okay? It's because there isn't just one average number. If you're using one fluorophore to measure your acidity and somebody else uses a different fluorophore to measure their acidity, they're gonna get different answers. And so, so one way to think of that is what if these blind men looking for the elephant, what if they stumbled into the zoo and they were all touching different animals, okay? It would just add to the confusion. One other point I want to make, and I'm getting very late here, I know that, is that sometimes when you're developing a new theory, you add a feature and that fixes a lot of the problem. So for instance, MEM1 was able to explain a lot of mixtures like oil and water, okay? And did a much better job. But then if you try to apply it to something like methanol mixing with acetone, where it's asymmetric, you get a really bad answer. So what you need to do is you need to go beyond that valley of death and go ahead and implement the full theory in the MEM2, and then you see that you actually have made a step in the right direction, but you have to make 2 steps instead of 1 to be able to get to the correct answer. There's another qualitative way that phase behavior is different with TPT1 I want to remind you of, and that is we can get closed loop phase diagrams with this theory. And so don't forget, we're definitely making progress here. Don't go back to that Ping Robinson business. So I've made a tabulation here of all the different parameters for different functionalities. And what you see is there is some correlation with these Camlet-Taff parameters. But again, we've got different observers, especially when it comes to the basicity, coming to different conclusions. And I think that's understandable. They're different blind men at the zoo. And so this is my conclusion slide. I just wanted to sort of highlight, okay, what are those master equations? And to remind you of, all we really need to know to solve any problem, protein folding or whatever, polyelectrolytes, is we just need to know the donor concentration and the acceptor concentration, and then everything else comes out. I've only demonstrated sort of grungy engineering properties here and some computational improvements, but I think there's a lot that can be done with density functional theory and thinking about much more complicated systems in maybe a little bit more approximate way once we've got these energies of acceptor and donor characterized. So thank you, and I'll open it up for any questions.